Welcome to Dungeon Academics. My name is Thomas and I will be your instructor. This video is the Big Question Part 1, Binomial Probability, a series in which we learn the mathematics behind our favourite games. Why am I making this video? Well, this is a mathematics lesson for everybody, but especially gamers. I think that a lot of people that play games have an intuitive understanding of the mathematics that goes on behind the scenes, but they might not have the necessary skills to explain that mathematics and take their understanding to the next level. So this is an attempt to teach people the maths that they may already have a slight grasp of. In addition, it's a way to learn mathematics in an accessible way. By using examples from games, you can see that the mathematics does make sense. It has applications rather than being a purely abstract piece of learning. And finally, I believe that by understanding the mathematics behind games, we can be better at those games. By having a grasp of what could happen or what might happen, we can make better choices in the games and enjoy them more. So, what is this lesson aimed at? What level? Well, binomial probability is generally in the high school curriculum, but middle school level maths is all that you need. If you have a basic understanding of arithmetic, you should be able to handle binomial probability. There is no complicated algebra, trigonometry, or calculus involved, just multiplying, dividing, and quite a few calculations, but nothing too exotic. This appears on the British A-level curriculum, though I believe some GCSE statistics curriculum have binomial probability as well. In Finland, it's on the Lukio curriculum, and in the International Baccalaureate, this is handled in the diploma program. I'm not so familiar with American curriculum yet, though I would guess it would also appear somewhere in the high school curriculum in the statistics modules. So, what is binomial probability? Binomial probability is how we deal with events that have two outcomes. We normally consider this to be a pass or fail situation, though anything when there are two specific outcomes, red or blue, heads or tails, can be covered by binomial probability. We just set one of the outcomes to be considered a pass and the other to be a fail, even if both are equally desirable. The other important thing is that an event is happening multiple times. We could be dealing with 5 rolls of a dice, 10 flips of a coin. The idea is that something is happening again and again, but each of those events is identical. The probability doesn't change, and previous outcomes don't influence the results of the next outcome. In the same way that rolling a 6 on a dice doesn't change the chance of getting a 6 on the next dice roll, flipping a heads doesn't change the chance of getting a head on the next coin toss. These are identical, independent events happening several times. Let's look at an example in the context of Dungeons and Dragons. I'm going to play the Dungeon Master and a character, the Barbarian. The corridor stretches ahead, a number of tripwires, trigger runes, and pressure plates visible. How do you want to move on? Oh, I'll go into a rage and then sprint down the corridor to clear all the traps out, making it safe for the rest of the party. Okay, I wasn't expecting that. I'll need you to roll 5 dexterity saves. The difficulty class is 18, and with your +5, you'll need to roll 13 or more on each d20 roll to succeed the save. Okay, can we use mathematics to work out what might happen and the more likely outcomes and the less likely outcomes? To break down the game mechanics into regular conversation, A saving throw is a roll that you make to protect yourself against something bad happening or to reduce the negative effects. It's made on a 20-sided dice. We abbreviate that to D20. The player needs to roll 13 or more to succeed. The difficulty class was 18 and they have a +5 modifier, so any roll of 13 or higher will become 18 or better. If you need to roll 13 or higher, there are 8 results on a D20 which would be considered a success. 8 in 20 can be simplified to 4 in 10 or 2 in 5. Probabilities can be treated as regular fractions and simplified in the normal way. Let's make a quick prediction using something called expected value. Expected value is a simple calculation we can do to tell us the most likely outcome. And to do that, what we do is we multiply the probability of an event by the number of times that event is going to happen. This only works for independent events, by the way. Independent events are ones where the previous outcome does not affect the probability of the next event. So, what is our expectation? Well, if there are 5 events and each one has a 2 in 5 chance of succeeding, we can just multiply those together. 5 times 2 in 5, we expect 2 successes and therefore 3 failures. So of those 5 traps, it is most likely that the barbarian will successfully avoid 2 of them and walk right into or run right into 3 of them. Now, we have a number of different scenarios for our outcomes here. The best case scenario is that somehow the barbarian manages to avoid all 5 of those traps or sets them off without taking any damage. That's the best case scenario, 5 successes. The worst case scenario, on the other hand, is 5 failures, that they blunder into each trap, set it off and take the full damage. But most likely we're going to get something in between those, a number of successes and a number of failures. We've determined that the most likely outcome is probably 2 successes and 3 failures, though it's going to be worthwhile considering all those different outcomes. Now, I've made this little diagram where I've spread out the 6 different scenarios. Now, the number of different outcomes is 1 more than the number of events. There are 5 events, so there are 6 possible outcomes, starting with 0 passes and 5 failures, and ending with 0 failures and 5 successes. An important thing to note is that the outcome of all 6 of these events must add up to 1. 1 represents totality, 100%. And in our calculation, if it doesn't add up to 100%, we may have made a mistake. Now, bear in mind, there might be some rounding errors. So if it comes to 99.9 or 100.1%, that's not necessarily a sign that you did something wrong. It just could be a rounding issue. But if you consider all the possible outcomes and it comes to 53%, there's definitely something missing. Either you've made some miscalculations or you've failed to consider a possible event. Okay, moving on. Let's consider the worst case scenario, 5 failures. We need to talk about arrangements here. With 5 failures, every single dice roll must fail. And there's only one way we can arrange this. Every single event must be a failure. Now, we talk about different outcomes. We talk about different combinations of results. We're going to use a little bit of mathematical terminology called combinations. We choose this 5 choose 0. That's 5 events with 0 successes. Now, it's often written 5C0, or it could be written 5 over 0 inside a pair of brackets. For anyone who's international at this point, I speak British English, obviously. Brackets are what often most people would call curved brackets or rounded brackets. Square brackets we call square brackets. So whenever I say brackets, I'm talking about the rounded ones. Whatever language, whatever convention you use, feel free to use it, but that's just the language that I use. Okay, moving on, let's look at the possible combinations or arrangements for 1 success and 4 failures. Now, it could be arranged so that the first roll is a success and the other 4 are failures. Or it could be that the first roll is a failure, then we get a success, and then 3 more failures. It could be 2 failures, 1 success, 2 more failures, and so on. Essentially, that 1 success could appear in one of 5 positions, the first, second, third, fourth, or 5th position. So there are 5 arrangements where we have 1 success and 4 failures. Each of these arrangements is equally likely. If we can find the probability of one arrangement, we can then multiply that by 5 because we know there are 5 different ways that this could happen. And we call this 5 choose 1. So 5C1 or 5 over 1 in the round brackets again. The next outcome, with 2 successes and 3 failures, there are a lot of different ways of arranging that. I've put them down here. There's 10 of them. But this is getting a little bit clunky. It would be nice if we could have a way of working out how many combinations there were without having to try and write them all down. And with only 5 different events happening, it got a lot. If we had 20 different events, this would be far too much to consider manually. Now, this is an entire field of maths called combinatorics. There's a lot of interesting things going on here, but I'm specifically focusing on combinations. Now, this can be found in one of several different ways. It can be found algebraically. So there's a little formula for it. You plug some numbers in, you do a calculation, you get the right answer. It can be generated using a piece of maths called Pascal's triangle, or your calculator might have a button for it. If you have a graphical display calculator or a scientific calculator with more functions than just addition, subtraction, multiplication, and division, there may be a specific button for combinations. It might be written as NCR. If you have that on your calculator, use it. Being a maths teacher and being quite mathy, I normally calculate this manually. There's a truism that after a while, you tend to calculate things in your head because reaching for your calculator and turning it on is more effort than just working it out. Maybe that's a maths teacher flex, but you have to let us show off every once in a while. Okay, Pascal's triangle. The first thing I need to point out, and this is quite important, is that this was not discovered by Blaise Pascal. This triangle was known and used by mathematicians throughout antiquity. We have evidence of it being used in China, in India and Persia, centuries or even millennia before Blaise Pascal was even born. Blaise Pascal was a French polymath, a mathematician, a physicist, and a contemporary to René Descartes, another great famous French thinker. The reason we generally call this Pascal's triangle is because he wrote a treatise on probability where he explained how he used this to solve problems much like what we are going to do now. So we name it Pascal's triangle in honour of the work that he did with it. That's not to say he was the first person to do that work, but he just wrote a very influential book. I know in other countries it's called other things. And learning the history of the piece of maths and how it's been used around the world is actually quite an interesting topic. But for now, I'm going to refer it as Pascal's triangle. There are a few important things to note about this. The first row, the top row of Pascal's triangle, is what we call the zeroth row. So it starts with a row 0 rather than row 1. If you look at how the triangle is formed, each cell is the sum of the two cells above it, with the exception of the outer layer, which only has one number above it. There is a pattern to the numbers. As you look at each row, they start small at 1, they get larger, and then they get smaller again. And this is always symmetrical. The number or pair of numbers in the middle are the biggest, and the numbers on either side get smaller and remain equal to their counterpart until you get to 1. The outside edge is always 1, and the second and second last number on a row is always equal to the row number. So looking at the fourth row, the first and last values are 1. Because it is the fourth row, the second and second last number is 4. And then the number in the middle, 6, is the largest one. Pascal's triangle can be really useful, but it takes a while to write it out. If you're doing a relatively small question with a small number of events, Pascal's triangle can be convenient to use, but I wouldn't want to have to write out the first 20 rows of this. Because if you are using Pascal's triangle, in order to generate the 20th row, you need to generate all 19 rows before it. So a bit laborious, but possible to use. Now, how does this relate to our problem with binomial probability? Well, each row represents the different outcomes for a certain number of events. The 0th row represents no events. There are no outcomes, no successes, no fails, so there's only one way to organise this. The first row represents one event. It could be 0 successes and 1 fail, or it could be 1 success and 0 fails. Those two cells, 1 and 1, tell you how many different ways there are of arranging this. The second row tells you about 2 events. The first entry is 0 successes and 2 fails. The second row tells you how many ways there are of arranging 1 success and 1 fail, 2. And the third entry tells you how many ways there are of arranging 2 successes and no fails. Only one way there. Important to note that each row has n plus 1 entries, because there are n plus 1 different combinations of events. The fifth row in this case has 6 entries representing all the possible outcomes from 0 successes and 5 fails to 5 successes and 0 fails. And again, this is impractical on a large scale, so I generally tend to favour an algebraic method or using a calculator. What about the algebraic method then? So, n choose r represents n events and r successes. 5 choose 2, or 5 over 2 in round brackets, represents 5 events with 2 successes. If there's 2 successes, then we also know there must be 3 failures, because the total number of events must be 5. We normally imply this, we don't have to write it down. 5 choose 2 tells us 5 events, 2 successes, and 3 failures, but we don't need to say the and 3 failures bit. To solve this numerically, we need to use a mathematical function called a factorial, and this is written as exclamation mark. 3 exclamation mark is 3 factorial. 5 exclamation mark is 5 factorial. And the way factorial works is you multiply the number by every natural number smaller than it all the way to 1. So 3 factorial is 3 times 2 times 1, which is 6. 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. You'll notice that these numbers get very big very quickly. There's a very reasonable chance that your calculator cannot calculate 100 factorial because the number is too big for it. Now, why does this work? How does this work? Remember, we're thinking about ways of arranging different events. Now, if we have 5 events, how many different ways are there of organising these 5 outcomes? Well, you have 5 positions for the first event, 4 positions for the second, 3 for the third, 2 for the fourth, and 1 for that last one. There are 5 times 4 times 3 times 2 times 1 ways of arranging 5 different events. If I had 5 tiles numbered 1 through 5, I could arrange those in 120 different combinations of events. But we're not arranging 5 different tiles. In the example that I've picked, we're arranging 2 successes and 3 failures. So instead of 5 different tiles, I have 2 with an S for success and 3 with F for failure. And the arrangement of the 2 successes relative to each other doesn't make a difference. They are the same event, a success. And each of those 3 failures is the same event. So we need to think how many of these arrangements is a duplicate, because we can just swap the successes, the position of the successes or failures. There are 2 ways to arrange those 2 successes. Wherever they are spaced in that arrangement of 5 events, I could just swap them around and it would be the same outcome. On the other hand, with 3 failures, there are 6 different ways to arrange those 3 failures. Now, it doesn't matter where those 3 failures are within the scheme of the 5 events. I can swap the failures round with each other without changing the outcome. So there are 6 ways to arrange those 3 failures. So, remembering that there are 5 factorial ways of arranging the 5 events, and 2 factorial ways of arranging the 2 successes, and 3 factorial ways of arranging the 3 failures, we end up with the equation 5 factorial divided by 2 factorial times 3 factorial. This tells us how many ways there are of arranging 5 events with 2 successes and 3 failures. In this case, 5 factorial is 120, 2 factorial is 2, 3 factorial is 6. That leaves us with 120 divided by 2 times 6, 120 divided by 12, and that is 10. There are 10 ways of arranging 5 events with 2 successes and 3 failures. Now, the general formula for this, n choose r, is n factorial divided by r factorial times n minus r factorial. N minus r tells us how many failures we have, given that there are n events with r successes. It's telling us how many events left over are there, which are all failures. So n factorial over r factorial, n minus r factorial. Your calculator probably has a button to do this, and if it does, in most circumstances, I would recommend you use that, unless you enjoy doing maths for the sake of doing maths, which obviously I do. I will probably do mostly this manually, but feel free to use a calculator if you prefer. Okay, let's continue with our barbarian trap problem. We now know that there are 10 combinations for getting 2 passes and 3 failures on this event. So let's now look at the probability of getting a pass and the probability of getting a fail. If you remember from the setup, I told you that the chance of them succeeding this check was 2 in 5. Logically, the chance of failing must be 1 minus the chance of success. In this case, 1 minus 2 in 5 is 3 in 5. So we know that we have a 2 in 5 chance for each event succeeding and a 3 in 5 chance of each event failing. So let's multiply that out. There are 2 successes, so we have 2 in 5 times 2 in 5, and we have 3 failures, so it's 3 in 5 times 3 in 5 times 3 in 5. We multiply each of these events together because the probability of 2 events happening can be found by multiplying them together. This gives us 2 times 2 times 3 times 3 times 3 all over 5 times 5 times 5 times 5 times 5. It is a complete coincidence that this can be simplified to be 2 squared 3 cubed over 5 to the 5th. It just happens to be that there are 2 2's in the numerator, 3 3's in the numerator, and 5 5's in the denominator. It's not always going to be a number raised to its own power. It's important to know that the numbers here come from the probability and the powers come from how many times this happened. There are a total of 5 events, which is why the denominator is to the power of 5. There are 2 successes, that's why there's a squared, and 3 failures, that's why there's a cubed. If we multiply these together, we get a result of 0.03456. That's about 3.5%. So each arrangement of 2 successes and 3 failures has about a 3.5% chance of occurring. But remember, there are 10 combinations for this. So we need to multiply that result by 10. And when we do, we get about 34.56% chance. So for our barbarian to dash down that corridor and set off 2 of the traps and avoid 3 of them, we have about a 35% chance. Looking at the general formula for this, there are 3 components. The first is the n choose r component. This tells us how many different combinations of this event can happen. Then there is p to the power of r. P is the probability of a success and r is the number of successes. So this tells us the probability of those successes occurring. And finally, there is 1 minus p to the power of n minus r. This tells us the probability of the failures. 1 minus p is the chance of a failure, and n minus r is the number of failures that occur. So, here's the formula again. It's worth paying a bit of attention to this. If you're taking notes, this is the one that you want to write down. N choose r times the probability of a success to the power of the number of successes, multiplied by the probability of a failure to the power of the number of failures. And remember, the number of failures is n minus r. Okay, so let's look at the other possible outcomes. Let's start at the beginning. 5 failures and 0 successes. We're going to start with 5 choose 0. Then we have 0 successes, so that's the chance of probability of success, 2 and 5 to the power of 0. And then we have 5 failures, so that's 3/5 the probability of a failure to the power of 5. Now, 5 choose 0, there's only one way to arrange 5 failures. They must all fail, so that's 1. 2/5 to the power of 0, well, any number raised to the power of 0 is going to be 1. So 2/5 to the 0 is 1. And 3/5 to the power of 5 is 243 over 3,125. When we multiply those together, we get 243 over 3,125, and that's about a 7.8% chance. So the chance of the barbarian failing every single check and taking the full damage from every trap is about 7.8%. I'm guessing the barbarian doesn't want that to happen. Moving on, now we can look at 4 failures and 1 success. So we're going to have 5 choose 1. There are still 5 events and we're choosing 1 success. The chance of getting 1 success is 2 and 5 to the power of 1. And the chance of getting 4 failures is 3 and 5 to the power of 4. When we multiply this together, we work out what 5 choose 1 is. 5. There's only 5 ways to arrange this. You can put the success in any of the 5 positions. 2 and 5 to the power of 1 is still 2 and 5. And 3 and 5 to the power of 4 is 81 out of 625. When we multiply these 5 components together, we get 810 out of 3,125. You may be tempted to simplify this fraction. They can at least be simplified by a factor of 5. I would consider not simplifying them. The previous probability was also a fraction over 3,125, and keeping a common denominator will allow you to compare the values more easily. Either way, I've also converted this into a percentage. The probability of succeeding once and failing 4 times is 25.9%, approximately. There's some rounding there. We've done 3 failures and 2 successes before. That was 34.6%. If we move on to 2 failures and 3 successes, well, we are now using 5 choose 3, 5 events with 3 successes. We're using 2/5 to the power of 3 for 3 successes and 3/5 to the power of 2 for 2 failures. Doing 5 choose 3 with either Pascal's triangle or n choose r gives us 10. This is the same as 2 choose 3, as 5 choose 2. These are the 2 central results and they are the same value. If you look at Pascal's triangle, many of the rows have 2 identical values in the middle when there is no single central value. We have to look at the probability of getting 3 successes, that's 2/5 to the power of 3, and then 2 failures, that's 3/5 to the power of 2. This gives us 8 over 125 times 9 over 25. We multiply those 3 components together again, we get 720 out of 3,125. Again, keeping a common denominator. This equals about 23%. Moving on, we consider 1 failure and 4 successes. We'll call this 5 choose 4. And because we want 4 successes, there will be 2 over 5 to the power of 4. And for the 1 failure, 3 over 5 to the power 1. 5 choose 4 is 5. If we can consider there's 5 events and we want 1 failure in there, so it can be in any one of the 5 positions. For our 4 successes, we have 2 over 5 to the 4th power, and for the 1 failure, 3 over 5 to the power of 1. So 5 choose 4 was 5. 2/5 to the power of 4 is 16 over 625, and 3/5 to the power of 1 is just 3/5. We multiply this all out, we get 240 over 3,125. And this simplifies to about 7.7%. Now, our last possible outcome is 0 failures and 5 successes, the best case scenario for our barbarian. So we're going to do 5 choose 5, 5 events with 5 successes. We want 2/5 to the power of 5 for the chance of getting 5 successes, and 3/5 to the power of 0 for the chance of getting 0 failures. Well, 5 choose 5 is just 1. All 5 events must succeed. 2/5 to the power of 5 is 32 over 3,125, and 3/5 to the power of 0 is 1. We multiply all those together, we have a 32 in 3,125 chance. That's about 1%. Quite unlikely. So we have resolved all 6 possible outcomes, from 5 failures and 0 successes to 0 failures and 5 successes. If we add up those 6 fractions, it does indeed come to 1. And if we use the percentage values, it adds up to 100%. Though, as I said, there may have been some rounding error, so 99.9% or 100.1% could have happened, but let's not worry about that. If we plot these as a graph, of course we love graphs here, you'll see that the most likely outcome is 2 successes and therefore 3 failures, which is what our expected value predicted. You'll also see that the results closest to that, 1 success and 4 failures, or 3 successes and 2 failures, are also the most likely ones. The expected value is, in general, the most likely outcome. Though sometimes when your expected value isn't a whole number, you might have to look either side of your expected value. If your expected value is 3.5 successes, well, that can't occur. So either 3 successes or 4 successes will be the most likely outcome. there has to be a little bit of interpretation of the results. But as you move away from your expected outcome, the probabilities do decline. It's not a symmetrical distribution. This isn't what we call normally distributed, but you can see there is a slight pyramid shape forming. So, what can we say about our barbarian? Well, as they run down the corridor, they are most likely to successfully dodge 2 of the traps and engage 3 of them. Whether that's good or not for the rest of the party, well, if they avoid those traps, then the rest of the party still has to deal with them. The rest of the party would probably want them to trigger all 5 traps and deal with the consequences of their own bravado. But the probability of the barbarian successfully getting down the corridor without setting off any traps was 1%. They're not really likely to happen. The chance of the barbarian triggering all 5 traps was, if I remember correctly, 7.7%? 7.8%. So again, that's relatively unlikely, but far more likely than a safe passage. And, importantly, our predicted outcome of successfully dodging 2 traps and setting off 3 is the single most likely event. By understanding this distribution of probabilities, we now have a good idea of what is likely to happen. Now, without understanding much maths, if you'd ask most Dungeons and Dragons players what they expect to happen, they'd be able to look at those numbers and say the barbarian's probably going to trigger 3 traps and dodge 2 of them. And that intuitive understanding of mathematics is useful. But now, by knowing about binomial probability, we can work out the relative chance of each of those 6 outcomes, and possibly we can use this knowledge to help shape our decisions. Now, I'm not saying that in the middle of the game you should get out your calculator and start doing these calculations. But what is useful is to have a mathematical understanding of what's most likely to happen and the relative likelihood of other possible outcomes. We now understand that the chance of getting 5 successes and 5 failures is comparatively small. We know that the most likely outcome is around the expected value, but the outcomes on either side are also quite likely. And this knowledge can help us make better decisions in the game. Okay, so as a summary of the method, where do we use binomial probability? Well, we use it when we have events with 2 outcomes, which we traditionally label pass or fail, where we are dealing with multiple identical events, where we are doing exactly the same thing several times. For example, flipping a coin, rolling a dice. We convert this into mathematical language. The number of events is n. The probability of a success is p, and we can find the probability of a failure by doing 1 minus p. There are a number of different outcomes equal to n plus 1, and we use r to represent the number of successful outcomes, and n minus r will give us the number of failures. Okay, let's do another worked example. Sister Aquitaine of the Adeptus Sororitas has been attacked by a mob of orcs. 8 attacks have hit and wounded her, but her battle plate armour offers excellent protection. For each wound sustained, on the roll of 3+ on a d6, the wound will be saved. Given that she has a wounds characteristic of 3, so the 3rd wound sustained will be fatal, what are the chances she survives this encounter? So, there are 8 events here. The number of wounds to be saved is 8. We can set n equals 8. The armour protects her on the roll of 3+ on a d6. So the probability of a successful event is 4 in 6. A 3, a 4, a 5, or a 6 are considered success. That's 4 in 6. We can simplify that to 2 in 3. The probability of a failure is therefore 1 in 3. 2/3 chance of success, 1/3 chance of failure. There are 9 possible outcomes. With 8 events, there are n+1 outcomes, ranging from 0 successes and 8 failures to 8 successes and 0 failures. For sister aquitaine to survive, the number of failures must be 0, 1 or 2. If 3 or more wounds get through, she does not survive this encounter. So we are going to set R to be 6, 7 or 8. 6 successes, 7 successes or 8 successes are the only way she will survive this. Let's look at her expected value. 8 events with a 2/3 chance of success. Well, 8 times 2/3 is 16/3 or about 5.3. We expect about 5.3 successes. Rounding, 5 successes means 3 failures. The prospects are not looking too good, but it will be close. Our expected value is, with rounding, just enough for her to fail the encounter and succumb to the wounds, but it will be close. Okay, so we're going to use this formula, n choose r, p to the power of r, 1 minus p to the power of n minus r. We've got Rn as 8 because there are 8 events. We have p as 2/3 and therefore 1 minus p is 1/3. And we are looking for all the outcomes where our random variable is 6 or greater. So we're going to set R to be 6, 7 or 8. So let's look at the possible ways of getting 6 successes and therefore 2 failures. So we're going to have 8 choose 6 times 2/3 to the power of 6 times 1/3 to the power of 2. What is 8 choose 6? Well, I wouldn't want to do Pascal's triangle for this. It's 8 rows, that's just too much to deal with. So I'm going to use the n factorial over r factorial times n minus r factorial. So 8 factorial on the top, 6 factorial times 2 factorial on the bottom. Now, I'm not going to calculate all of this. I don't need to calculate 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 for the numerator, and 1 times 2 times 3 times 4 times 5 times 6 times 1 times 2 on the denominator. What you may notice is that the sequence 1 through 6 appears in the numerator and denominator. And because everything is multiplied together, they just cancel each other out. That leaves 7 times 8 on the numerator and 1 times 2 on the denominator. And because multiplying by 1 does nothing, I'm going to skip that as well. I'm just left with 7 times 8 over 2, and that's 28. So there are 28 ways of arranging 6 successes and 2 failures. Knowing that, I can look at the probability parts. 2/3 to the power of 6 is 64 over 729, and 1/3 squared is 1 over 9. We combine these 3 components together, 28 times 64 over 729 times 1 in 9, and we get 1,792 over 6,561. So that's about a 27.3% chance of passing 6 saves and failing 2. Moving on, let's look at the chance of her passing 7 fails and failing 1. So n is still 8, p is still 2/3, and now r is 7. So I have 8 choose 7 times 2/3 to the power of 7 times 1/3 to the power of 1. Again, I'm going to use n choose r algebraically to calculate the number of combinations. It's just going to be the products 1 through 8 divided by the products 1 through 7 times 1. And again, we can use that simplifying trick, and it simplifies to 8 over 1, or 8. There are 8 ways of arranging 7 successes and 1 failure. So we have 7 successes, so that's 2/3 to the power of 7, and 1 failure, so that's 1/3 to the power of 1. We multiply all these together, we get 1024 over 6561. Now we can look at the probability of getting 8 successes out of 8 events. So n is still 8, p is still 2/3, and r is now 8. We want 8 successes. 8 choose 8 is just 1. N choose n is always 1. There's only one way to arrange 8 successes out of 8 or 12 successes out of 12. We look at the probabilities. 2/3 to the power of 8 is 256 over 6561. And the chance of us getting the probability for 0 failures is 1/3 to the power of 0, which is just 1. So the probability we have here is just 256 over 6561, because the other components are 1. Multiplying by 1 doesn't change anything. So we have about 3.9% chance of passing all 8 saves. Now, we add these 3 events together to find her chance of surviving these 8 attacks, and we get a 46.8% chance of survival. So that's less than 50-50. Now, we said they weren't looking great, but it was going to be close, and this fits in with our expected value perfectly. She has less than a 50% chance of survival from those 8 attacks. Those are not great odds, but it's not impossible. I believe that doing an expected value estimation at the start of these binomial probability questions is quite useful, because it's a good way to gauge whether our answer is close. By having an idea of what we might get, it will allow us to spot mistakes we may have made, go back and fix them. Okay, let's look at one more example together. Riplikish, the elven sword saint, will be making 9 attacks with his greatsword. Each attack hits on a roll of 7+ on a d20. What are the 3 most likely outcomes? Let's use the power of maths to predict what's going to happen here. So we have 9 events. We're going to set n as 9. A hit roll of 7+ means results 1 through 6 miss and 7 through 20 hit. Therefore, the probability of getting a hit is 14 in 20 or 7 in 10. And the probability of getting a miss is 6 in 20 or 3 in 10. There are n+1 outcomes, so 10 outcomes, ranging from 0 hits to 9 hits. Our expected value is 9 times the probability of a hit, which is 7 in 10, which is about 6 hits. So our most likely value is probably 6 or 7 hits, and we're needing to find the 3 most likely outcomes. So what we're going to do is we're going to start with 6, and we're going to start checking on either side. So we do 6 and we do 7, and then probably 5 or 8 are going to be our next most likely outcomes. We'll see what the results say and add up the 3 most likely ones. And again, we can set up the formula. We've got n choose r at the start. We've got the probability of a hit multiplied by the number of hits, and then the probability of a miss multiplied by the number of misses, n minus r. Okay, there's a lot of numbers on this slide. Let's break down what's happening. 9 choose 6. Well, I'm going to use the same shortcut as before. I know that's just going to be equals 7 times 8 times 9 over 1 times 2 times 3, but please use n choose r in a calculator if you have access to it and you don't fancy doing this arithmetic. But it tells me there are 84 ways of arranging 6 hits and 3 misses. The probability for getting 6 hits is 7 out of 10 to the power of 6, and the probability of getting 3 misses is 3 in 10 to the power of 3. Now, those are quite large numbers. I definitely multiplied these together with a calculator, and I got 266,827,932 out of a billion. And that's about 26.68%. So pretty close. Let's look at 7 hits. We're going to do 9 choose 7 to give us the number of combinations, and that's 36. To find the probability for those hits, we do 7 in 10 to the power of 7. And to find it for the number of misses, we do 3 in 10 to the power of 2. We multiply that all together and we get 266,827,932. That's exactly the same number as we got for the last one. Now, if something like this happens to me, my first reaction is, hang on, should those be the same numbers? Have I made a mistake here? Have I just pressed the same numbers again on the calculator? I want to stop and check this. And it turns out that they are exactly the same. This isn't a coincidence. This is real. How can this be the case? I have a philosophy when I'm teaching maths, and that is everyone makes mistakes. To make mistakes is human. But being good at something means you can spot those mistakes and then you can go back and fix them. And the fact that these two numbers were the same for me triggered my, is this right response? So let's go back and have a look. Why are these the same? Well, the first thing I want to talk about is the n choose r components for 9 choose 6 and 9 choose 7. When I bring these up, you'll see that the difference is that with 9 choose 6, there's an extra 7 on the top and 3 on the bottom to give the different results of 84 and 36. You should see that this factor of 7/3 is important. There's a 7/3 difference between the two of them. Also, when we have 7 hits, we have an extra hit to consider, 7 in 10, and 1 less miss, 3 in 10. So we're multiplying by an extra 7 in 10, but dividing by 3 in 10. 1 extra hit, 1 less miss. 7 in 10 times 10 over 3, I've inverted it because it's a miss, is 7/3. There's that number again. So the extra 7/3 we get from having 9 choose 6 is exactly counted out by the 7/3 we get for having an extra hit and 1 less miss when we have 7 hits. So there's a extra 7 in 3 that appears when we have 6 hits, and an extra 7 in 3 that appears when we have 7 hits. And that means that the two results are identical. They're the same. They're supposed to be the same. I find that quite pleasing. So our result is correct. They are the same values. Okay, moving on. Let's look at 5 hits. 9 choose 5. Well, there's 126 ways of arranging 5 hits from 9 events using 9 choose 5. The probability of getting 5 hits will be 7/10 to the power 5. And the probability of getting 4 misses will be 3/10 to the power of 4. When we multiply all of these together, we get another big number, over 1 billion, but it's about 17.15%. There we go. So far, we've found probability for 6, 7, and 5 hits. It could be the case that 8 hits is more likely than 5 hits. We know that 4 hits is less likely than 5, but it could be the case that 8 hits is more likely than 5, and we want the top 3 results. So let's check the probability of getting 8 hits as well. Well, that's going to be 9 choose 8, and 7/10 to the power of 8 for 8 hits, and 3/10 to the power of 1 for 1 miss. We multiply all that all together, we get 15.56%. This is a little bit less than the probability for 5 hits. So we know the 3 most likely outcomes are now 5, 6, and 7 hits. We're not going to bother with 8, it's not in the top 3, and the question only asked for the top 3. Okay, let's add those top 3 results together. 5, 6, and 7, we add them up, we get 70.5%. The probability of Riplikish scoring 5, 6, or 7 hits is a little bit more than 70%. So he's consistently likely to hit 5, 6, or 7 times in his turn. That's pretty good. So one more time, let's summarize when we can use this and how we use it. Firstly, we're looking for events where there are two outcomes which we can label pass or fail. They don't always have to be a good outcome and a bad outcome. It could be red or blue. We just consider one pass and one a fail. We're looking for events where there are multiple independent events, where the same thing happens several times and the probability does not change between events. And the typical examples for this are things like flipping a coin or rolling a die. The method for this, well, we're going to need to define some numbers. N is the number of events. P is the probability of a success, and therefore 1 minus P is the probability of failure. We always have a number of different outcomes equal to N plus 1. And we use R to represent how many of those events are going to be a success in each outcome. The formula we use is N choose R multiplied by P to the power of R multiplied by 1 minus P to the power of N minus R. What next? Okay, I've actually written 6 homework questions that you can try at your own pace at home. I will put the answers in a pinned comment to this video, so give them a go and see if you got them right. There are other videos that I do that explore some quite interesting maths through the context of Dungeons and Dragons. You might be interested in the video The Fireball Fiasco, that's 001, or the reroll recalculation 004. There's some quite interesting algebra and statistics in those videos. They're not actually maths lessons, they're explorations of maths. The next video I'm going to make in this series will be on trinomial distribution. That's where there are 3 possible outcomes to an event. That's really useful in Dungeons and Dragons, where you have attack rolls that can have a miss, a hit, or a critical hit. And where a critical hit is really important to your character, knowing the possible distribution of events becomes quite useful. A bit about me. Well, as I said, my name is Thomas. I'm a maths and physics teacher based in Helsinki, Finland. I love playing games. I love board games and tabletop roleplay games. Those are my favourite. I play a lot of Dungeons and Dragons as well as other games as well. And I have a long history with the Warhammer hobby as well. So that's why all my examples came from Dungeons and Dragons or Warhammer. I love exploring how mathematics shapes games, both how we play them and how we design games. And my channel is an exploration of the maths in games and how we design games as well. So if you like the details of game mechanics, I have a lot of videos discussing that. Many of them are not as formal as this. They are more discussion videos. This is definitely a maths lesson video. After this, I will give you 6 questions. Feel free to pause the video and do the questions. There's a summary of the method again on the last slide. But that's pretty much all the talking that I'm going to do for now. I will let you continue and give those homework questions a go. I like to end my videos exactly the same way, and I'll do that for this as well. Enjoy your next game, whatever it may be.